OS. The security of Android OS is a major challenge, as Android is a very popular mobile OS. Its demand is increasing day by day with the increase in the challenge to safeguard an app installed on users' device which is connected to world of internet most of the time. These devices are more prone to attacks by the apps installed on their device called malware. The report says that Android OS is the first choice for malicious software designers to attack Android OS. A solution to avoid these malware is presented in our project. A very warm greetings to everyone. We, the team Code Blooded, are participating in the Smart India Hackathon 2023. Our problem statement number is 1381. And the topic is the analysis of malicious mobile applications given by the Ministry of Power. Different methods for doing malware analysis are static and dynamic approaches. Static analysis is based on the program source code. It has maximum advantage of exposure and it helps to analyze the source code broadly. However, static method is based on source code. And if we cannot get the target source code through decompiling or reverse engineering, it is hard to analyze the program accurately, especially in the occasion that the target program has been a malicious file. Dynamic analysis points to the exploration of runtime performance by running the program. This type of method is precise for finding the actual malicious code behavior. Meanwhile, the dynamic method has its own disadvantages because of its inadequate execution exposure. That is to say, we cannot guarantee all of the running paths have been triggered during the test. In this paper, we present a combination of static and dynamic security analysis model that can make up for their shortcomings with each other, performs the analysis of malicious performance more widely and correctly. Figure 2 explains the whole steps. Before analyzing the Android application APK, Android application package needs to be decompiled to get the corresponding configuration and SMALI 11 files. Among them, the configuration file with the format of Android manifest XML is mainly used for permissions filtering stage, and the SMALI files are mainly applied to dynamic monitoring module. First of all, we choose those suspicious applications with great potential to leak users' privacy. Then, if a program is suspicious, enter into the dynamic monitoring module, where input the target SMALI codes, embed some tracking code, repackage and resign the APK. In future, once the APK is running, we can dynamically monitor the behavior of privacy leakage and give immediate alarm for users. And those alerts or logs can be used for further detailed analysis manually or automatically. Next, we will discuss the three core components of the framework: APK static decompiler, permission filtering module, and dynamic monitoring module. APK static decompilation. With the increase in the D before permission filtering and dynamic monitoring, we need to extract the Android applications Android manifest, XML file and small files equivalent to the target APK. The Android application is an installation package ending with suffix .apk, an acronym for Android package. APK is the same as to .exe, executable, file in the computer. After installation, it can be executed in Android OS immediately. APK is actually a compressed file compliant with the zip format, which can be extracted by popular .zip compatible decompression tools. In addition, it must be noted that most applications are code obfuscated, and the unzipped file is not able to be analyzed directly. Permission module. There is some permission that may not exist risks by itself, but combination of permissions may exist a security risk. For example, an application applies for permissions to read phone state and sending messages, and there may exist risk of transfer the phone number or IMEI out. Permissions module is based on a set of security policies to find out whether an application has some special risk permission combinations. For all the Android permissions, there are 4 types of security levels. Those are normal, dangerous, signature, and Signature or system. Dynamic monitoring module. We apply real-time monitoring by inserting monitoring code to the decompiled APK. The Android developers write the application in Java, compiles it into Java bytecode, and finally transfers to the Dalvik bytecode, which can be executed in DVM. So it's easy to do reverse engineering by converting the Dalvik bytecode to Java byte code, then rewrite the Java bytecode, and finally convert the rewritten Java bytecode back to Dalvik byte code. Still, this type of method does not work all the time. There are quite a few significant differences between Java Virtual Machine and Dalvik Virtual Machine. JVM is based on stack, while DVM is based on register. A number of tools are available, such as dex2jar 11 and DED 7, which will convert Dalvik bytecode to Java bytecode. Still, this is not a lossless converting. Some information from the Java bytecode is lost when being converted to Dalvik. These tools try to gather the lost details based on the context, but at times the inference is defective. Even while these errors does not prevent static analysis on the converted Java bytecode, in our experience they often lead to invalid Java bytecode or later invalid Dalvik bytecode. After we convert an application's Dalvik bytecode to Java bytecode, e.g. dex2jar, and then back to Dalvik bytecode, the resulting application does not run properly. So the possible way is to directly use the Dalvik bytecode. Smally and backsmally are two assembler and disassembler, respectively, for the DEX format used by the DVM. Smally is an intermediary depiction of Dalvik bytecode. Smally can fully realize all the features of DEX format, annotations, debug information, thread information, etc. Moreover, DEX and Smally can convert lossless between each other. In this paper, we try to directly rewrite Dalvik bytecode, insert the monitoring Smally bytecode into the decompiled Smally files. We can obtain Smally files from the static decompiling. Then locate the concrete position of the sensitive API, and insert monitoring Smally bytecode to each dissimilar susceptible API. After that, we use apptool to repackage the modified Smally bytecode to create a new .apk and use the signature tool to re-sign it. Running the new APK. On Android emulator, we can use logcat to view the runtime logs. It can generate a log on SD card which records the detailed call information. We proposed a two-step analysis of Android apps, static and dynamic. At the initial stage, the permission-related issues of applications are highlighted. The permission mechanism of Android OS provides the facility to access all the required details during installation, and once accepted the permission can't be modified. 2. Stop this, we use two mechanism, i.e. static and dynamic methods, to analyze the behavior of to find apps are malicious or not. We use reverse engineering tools through which the .apk file is converted to .class file and the code is analyzed and changes are made, and then it repackaged again using Smally bytecode, which is an intermediate code of APK file. This Smally code is inserted into process for monitoring purpose. This method can be used at wide scale for monitoring service automatically. Further research will continue for monitoring the sensitive API in Android and explore the vulnerability of the apps. At the same time, to provide more dynamic analysis methods to conduct more research.